We're going to learn something called implicit differentiation, which is really just a fancy application of the chain rule, although it might not look that way to you. So before I talk about implicit differentiation, let's think about these two statements. So suppose I told you, make sure you know the chain rule for class on Friday. That's an implicit statement. I'm not telling you exactly what I mean by that, but what you might infer from it is that there might be a quiz on Friday. An explicit statement would have been, there's a quiz on Friday. So the implicit statement is kind of hiding its meaning a little bit. And so that's what we're going to be doing here. All the functions that we've been working with so far are explicit functions. They've been given to us in the form y is equal to something, y is equal to some function of x. With implicit expressions or equations, we are not going to necessarily be given y is equal to a function of x. We might be given something like this, not of the form y is equal to something. So this is an implicit expression. It is inferred by this expression that y is a function of x, but we are not actually told what function of x it is. This particular example is easy to rearrange. We could rearrange this so that y is 3 minus x. This is an explicit expression because it tells us exactly what function y is equal to. It's equal to 3 minus x. Okay? So that was easy. If I wanted to take the derivative of this function, if I want to find dy dx, I just rearrange things and I find the derivative. So y prime is just -1. Okay, that's easy. We could be done now. But I promise examples get more interesting. So what if we look at these other examples here? So once again, these are both implicit expressions. Y and x's are all mixed together. We're not given y is equal to one particular expression. If we wanted to get an explicit expression for this first one, I could rearrange this. So I get y squared is 4 minus x squared. So y is the square root of 4 minus x squared, or negative square root of 4 minus x squared. This one's a little messier than the first one because I start out with a single expression and I get two different expressions for y. So if I wanted to take the derivative of y, I would have to take the derivative of both of these. Okay, it might be a little bit easier if I could leave the expression like this and just take the derivative instead of having to rearrange things first. And if I look at this last example, or this next example, I have a y cubed and I have an x times y. If I try and solve this expression for y, I'm going to really struggle. I'm not going to be able to do it. I can't solve this for y. So I cannot get an explicit expression. I cannot get y is equal to some function of x in this case. It is inferred that there is some expression. I just can't figure out what it is. And so my question, or our question for today, is can I leave my equation like this, but still find y prime? And the answer is yes. Otherwise, we wouldn't be doing this. Okay, so let's think about how we do this. So let's start out, and we're going to do this for this example, but only this example. And then we'll figure out how to do this without quite so much work. So by writing this implicit expression, we are implicitly thinking that y is some function of x. We could call it f of x, but it's a little bit nicer if we call it y of x for later on. So what I'm going to do is I'm going to rewrite this whole expression, just replacing y with y of x. That's the step that we're not usually going to take, but it's useful to see why. It's useful to see here first. So I'm going to replace y cubed with y of x, that whole thing cubed. The x cubed stays alone. I have 6x, and then that's equal to 6x, and I'm going to replace that y with y of x. Okay, so remember our goal here is to find dy over dx, which is y prime, which is y prime of x. All same notations, or different notations for the same thing. Okay, so what we're going to do here is we're going to leave this expression alone. We're not going to try and rearrange anything, and we're just going to take the derivative of both sides of the expression. Okay, this is how implicit differentiation works. Okay, so now I have like lots of pieces that I have to take the derivatives of. Some of them are easier than others. So I'm going to start with the easy pieces. The derivative of x cubed behaves the same as it always does, 3x squared. Okay. And I'll jump around. Let me take the derivative of this piece here. So that I have a product there. I have 6x times another function. So I'm going to treat this as 6x times y of x and use the product rule. The derivative of 6x is just 6 and leave the y of x alone. Now I leave the 6x alone. The derivative of y of x is just y prime of x. That's the thing that we're eventually trying to find. Okay, and so we have one last piece to deal with. We have this piece here. I need to use the chain rule on that piece because I have a function inside of a function. So for the chain rule, my outside function here is x cubed. My inside function is y of x. The derivative of x cubed is 3x squared. The derivative of y of x is just y prime of x. So here I'm going to get 3y of x squared times y prime of x. And let me do a little side note here. Let's notice that if I didn't write the y of x there, what I would have gotten there is 3y squared times y prime. What we notice is if it was just an x cubed that we were taking the derivative of, its derivative would be 3x squared. The only difference here is that we're getting this y prime. And that's going to be what happens with all of these. We're going to get these extra y primes floating around, and that's always coming from the chain rule, even if we don't always write that out. Okay, so we've done the hard part now. We've taken a derivative. Now we need to solve for y prime. Okay, so this is actually the algebra step, but it's the step that most calculus students struggle with the most. Okay, so I'm going to solve for y prime of x. Which means I'm going to get all the y primes together on one side of the equation and everything else on the other side. Doesn't matter what side you choose to move the y primes to. I'm going to move them to the left. So I'm going to leave the 3y of x squared times y prime of x. Subtract this over. That'll be equal to 6y of x, and I'll subtract that over. Okay, now I can factor a y prime out from this side. That was the whole point there. So I'll factor y prime of x out. Get left with 3y of x squared minus 6x. This step can be tedious. Leave this side alone. So y prime is, I'm going to divide both sides. Minus 3x squared divided by this mess. Okay, and I've actually finished. I'm going to go ahead at this step. I'm going to go ahead and replace all that y of x just with y because that was what we originally had. So I get y prime is 6y minus 3x squared over 3y squared minus 6x. And that is my answer. It's okay that my answer has x's and y's in it. Okay, we'll do one more example. And if you need help understanding this in class, we'll do lots of examples. Okay, let's do one more example. And we'll treat this kind of more in the way that we'll normally treat these. So we've got x's and y's mixed together. That tells me I need implicit differentiation. So what do? I need to start out by taking the derivative of both sides of this expression. Okay, I am not going to rewrite y as y of x in this example. I'm going to leave it as y, but we want to think in the back of our minds that y is a function of x. Okay, so now I need to take the derivative of everything. The derivative of 1 is 0. It's going to go away. The derivative of 3x is 3. And now I get to deal with the more interesting pieces. So 8x cubed. Let's think about how I take the derivative of that. So I'm going to take the derivative like I normally would if it was an x. So I would get 8 times 3, which is 24. So I'd have 24y squared. But now remember, y is a function of x. So I can't just stop here. I need to multiply by a y prime. And that's coming from the chain rule. If I treated this as 8y of x cubed, I would do the chain rule. At the end of the chain rule, I would multiply by the derivative of the inside function, which is the y prime. So that's where that y prime comes from. But you can also think anytime I take the derivative of something that has a y in it, I get an extra y prime. Okay, so let's look at this piece now. I need the product rule on that. The derivative of x cubed is 3x squared. Leave the y to the fifth alone. Now I leave the x cubed alone. The derivative of y to the fifth is 5y to the fourth, just like it normally would be. but times y prime, because y is a function of x. Okay, so I've done the hard stuff, I've done the calculus, now I just need to do the algebra. So I'm gonna get all, well, I'm gonna get all the y primes together. So I've got y prime, and then I've got everything else. So I'm just gonna go ahead and subtract this piece over to the other side. So I'm going to be left with 3x squared y to the 5th plus 3 is equal to 24y squared y prime plus, I'm going to rewrite that as 5x cubed y to the 4th y prime. Okay, now I can factor a y prime out of this side of the equation. So I have y prime times 24y squared plus 5x cubed y to the 4th is equal to that stuff from above, and I'm being lazy, so I'm not going to rewrite it. Now I divide both sides by this expression. So I have 3x squared y to the 5th plus 3 divided by 24y squared plus 5x cubed y to the 4th.